Every physical object has mass. It is a fixed property, representing the raw amount of matter inside an object, and it determines how much that object resists a change in motion. Weight, however, is a separate property entirely. It is the downward force exerted on that mass by gravity. To see the difference, look at an astronaut in deep space. Far from any planet, their 75-kilogram mass is weightless. 0 newtons of force are acting on them. Place that same 75-kilogram astronaut on the surface of the Earth, and gravity pulls downward on them with a force of 735 newtons. The mass remains identical, but the weight changes depending on the environment. To find the weight of any object on Earth, we take its mass in kilograms and multiply it by Earth's standard gravitational acceleration, which is 9.8 meters per second squared. Multiply that mass by 9.8, and you get the weight in newtons. The official requirements for your exam state clearly that you must know how to define gravitational field strength as force per unit mass. This means you must be ready to use the equation rearranged as G equals W divided by M. From mass, we can derive density, the amount of mass packed into a specific volume. For regular solids like a cube, you find the volume using a ruler and simple geometry. For a liquid, you pour it into a measuring cylinder to find its volume, and use a balance to find its mass. Divide mass by volume, and you have your density. Mass, weight, and density form the baseline properties of matter. By measuring these 3 values, you have exactly the information you need to predict how an object will interact with its physical environment. We can measure the volume of a perfect cube easily, but if you are handed a jagged rock or an oddly shaped piece of metal, a standard ruler is useless. You need a different technique. In the displacement method, we partially fill a cylinder and record the level at 50 cubic centimeters. Submerging our irregular object displaces the water, raising the volume to 83. Subtracting the initial reading from the final leaves a solid volume of 33 cubic centimeters. By combining a simple cylinder of water with basic subtraction, the displacement method gives us the exact volume of any irregular object. With that volume in hand, calculating its density is just one division step away. When an external force acts on an elastic object, like a spring, the material stretches in a predictable way. This is Hooke's law, which states that the force applied, F, is equal to the spring constant, K, multiplied by the extension, X. Plotting applied load on the y-axis against extension on the x-axis produces a straight line, showing they are directly proportional. But adding too much weight curves the graph upward at the limit of proportionality. Past this junction, the spring becomes permanently deformed. Let's test this. If a 14-newton load causes a 0.04 meter extension on a linear spring, what is the spring constant? Pause to calculate it. Rearranging Hooke's law, we divide the 14-newton force by the 0.04 meter extension, giving a spring constant of 350 newtons per meter. Identifying the limit of proportionality is a standard requirement for your exam, because it marks a strict boundary in mechanical engineering. The exact moment a temporary stretch becomes a permanent failure. When an object rests on a surface, its weight exerts a downward force. Pressure is the measure of that force spread over a specific area. We calculate it by dividing the total force in newtons by the area of contact in square meters. Liquids exert pressure too, but we calculate it differently. Liquid pressure relies on the density of the fluid, the strength of gravity, and the depth of the fluid. The most common trap here is using the wrong units for depth. This diagram illustrates a standard exam scenario. We have a block resting at the bottom of a water tank. The water has a density of 1,000 kilograms per cubic meter, and the block is at a depth of 40 centimeters. We need to find the liquid pressure acting on the block. You cannot use centimeters in this formula. Before plugging any numbers into the pressure equation, you must convert the depth to standard SI units by dividing by 100, so 40 centimeters becomes 0.4 meters. Now we apply the liquid pressure formula, density times gravity times height. That is 1,000 multiplied by 9.8 multiplied by 0.4. This results in a final liquid pressure of 3,920 pascals acting on the block. Pressure pulls all of our prior mechanics concepts together. To find it, you must correctly apply mass, account for the exact force of gravity, and properly measure the dimensional space the object occupies. Fluency in these 5 core mechanics formulas is essential for solving any standard physics paper. Mastery of these equations allows you to calculate exactly how objects behave under gravitational, elastic, or fluid stress. This cheat sheet collects those equations. You know how to convert mass to weight. You can calculate density for both regular and irregular objects. You can map Hooke's law up to the limit of proportionality, and you know how to compute pressure for both solid blocks and fluid depths. To lock these concepts in, you need to practice them. Head over to www.studybuddy.tech to take your free diagnostic test. It will immediately pinpoint the exact formulas you need to review and build a customized study plan just for you. Keep practicing, and I'll see you in the next lesson.